This presentation aims to investigate how temperature changes affect the phenomena of Coulomb damping. To do so, the reality of vibration and damping must be understood first.
The case study was broken up into three parts. Part A involved creating a code that modeled Coulomb dampening, which highlights the effects of time and displacement of a spring attached block. Part B investigated the effect of manipulating different variables to determine how they could affect the modeled amplitude losses. Finally, Part C, similar to Part A, looked to model the reaction in Coulomb dampening. However, in the presence of a harmonic excited force. We'll start by evaluating the mathematical concepts and describing the code that captures this model, as given in the respective case studies.
It is universally recognized that vibration is generally a reference to the periodic oscillating motion of a particle or body about its statically equilibrium position. We know too that many mechanical systems and structures experience a vibration phenomenon as a result of mass imbalance, misalignment, uneven application of friction, and many other factors. And it is normally considered undesirable because they create increased stress and energy losses on the system that prove economically detrimental. To combat these undesirable vibrations, a process known as damping is introduced to restrain the vibrational motion by dissipating this energy in different ways. As evidenced in the introduction to the case study, Coulomb damping specifically, also known as dry friction damping, is a common process incorporated in many mechanical systems to dissipate vibrational energy because of its mechanical simplicity and convenience. As evidenced in the given figure, there are merely two forces applied to the block in the horizontal or X direction. The forces exerted by the spring and the opposing frictional forces. By incorporating Newton's second law of motion, which highlights that the acceleration of an object is produced by a net force is directly proportional to the magnitude of the net force and inversely proportional to its mass. Due to the oscillating nature of the spring system, the frictional forces must be considered in both positive and negative instances, as highlighted by the following relationship. After a sign convention is established, we then have the following ODE through transposition, which, when initial conditions are considered, defines the relationship between displacement of the block and time.
The first 7 lines of the code define explicitly the variables used in the relationship. The T bracket X refers to an approximate solution to a single initial value ODE that is solved in the range of T span and X0 variables and returns the right side of a symbolic equation. The next 3 lines of code are merely the instructions to plot the given function with appropriate axis labels. The function f equals RHS calls the ODE into the ODE solver and solves it between the given range. F1 equals Y1 and is stated to equal Y2. Y2 is then substituted into the equation at the instance of X bar. Y1 is substituted at the instance of X. Put simply, Y1 is made equal to X, then Y2 becomes X bar, which is given as the function shown. In similar fashion, code C models a Coulomb dampening system, but in the presence of a harmonic exciting force. This force is incorporated into the ODE by re-evaluating the experienced forces of Newton's second law. The code C is similarly organized as in code A. However, the functions are changed to implement the harmonic exciting force into the respective ODEs. The main change is function F, which equals force T. F is then said to equal F0 times sine omega T. This is then implemented back into the F2, creating that equation.
The graph on the left is taken from a research paper titled Thermal Degradation of Extension Springs and models the effects of increased temperatures on springs. The parameter that we will consider for temperature dependence is the spring constant K. Evidently, in the graph on the left, as the temperature exceeds 500 degrees Celsius, the spring constant is reduced in an inversely proportional manner. To extrapolate this data, polynomial fitting had to be manipulated. The code that illustrates this relationship is given in the following program. The Z values increase at increments of 50 and the corresponding Y2 values are recorded from the graph and converted from pounds per inch to newtons per meter rather. This data is fitted to a cubic function using the polyfit function. The x value specifies the range that the polyfit is extrapolated to. Polyval specifies the values of y at the different values of x. These calculated values are now the spring constant values k at varying temperatures. The remaining code merely plots this relationship and identifies relevant x and y axes titles.
Before a comparison can be made of the effects of temperature on the nature of Coulomb dampening, the mass of the block must be changed to meet the specifications of the spring under analysis. The original case study has a spring with a constant of 70,000. This spring can take a considerable amount of weight compared to the spring investigated in the paper used. Therefore, the mass of the block was taken from the paper to validate the credibility of the data. The paper states the spring were extended to a force of 0.294 pounds, which converts to 0.1334 kilograms. This is the mass considered when comparing temperatures of which correlates to the respective spring constant investigated. To call these effects into the function, the same polyval and polyfit functions were used. When the code is run, the user is asked for an input of the original temperature. The spring constant K is then identified at this temperature, and the ODE is solved considering the spring constant. The command window prompts the user for a second temperature, and the same process is conducted as for the original temperature. To plot this relationship, the tiled layout command is used, allowing for both temperature instances to be plotted side by side.
The corresponding graphs illustrate the effect of temperature on Coulomb damping. Evidently, as temperature increases, the time taken for the block to reach zero displacement decreases. This is shown by the highlighted red shapes in the slide. The following graphs are related in that they highlight the amplitude losses experienced by the graphical model illustrated in the previous slide. Whilst these graphs visually do not show much difference, if you determine their respective gradients, it can be seen that at 800 degrees Celsius, the amplitude loss is greatly increased, and hence the displacement between the cycles reduces drastically. We are now to consider a similar phenomenon, but in the presence of a harmonic exciting force. As highlighted in red, the only changes to Newton's second law, which is then expanded to an ODE, is in the presence of this exciting force itself. The variables for force and omega had to be varied to attain the following relationship. The relationship between displacement and time remains the same between both the case study and the model obtained through MATLAB, despite a variation in amplitude. Nevertheless, it is inevitable that the general arrangement of both relationships is virtually identical. When the variables are kept at a force of 500 newtons and omega set to 10, the displacement can be seen to greatly increase. When comparing the effects of temperature on such a system, it is clear that as temperature increases, so does the magnitude of the displacement of the block from its original position.
It is inevitable from the results discussed that temperature has a substantial effect on the performance of a Coulomb dampened spring system. As temperature increases, the spring experiences a process of softening. This phenomenon can be explained on an atomic level, as increases in heat result in the excitation of atoms, causing them to break from their structural groups and become more uniform, and ultimately increase in malleability. Krieg is a malefactor that influences the efficiency of such a system at increased temperatures, as is evident in the table below, which evaluates the integrity of springs at different temperatures. It is evident that the spring is stretched in nature, which influences strength and ability to stand loading. You can see that the new springs are quite densely packed together, with the coils having very little gaps between them. However, as the temperature increases, the coils become more spread out, and this in part increases the amount of creep the spring can withstand, or so reduces the amount of creep the spring can withstand, and also reduces the strength.
When considering the relevance of this phenomenon in real-world applications, it becomes extremely important to determine a temperature range that serves to its optimal performance. The graphs represented show a comparison of the relationship between displacement and time at temperatures of 25 degrees and 200 degrees respectively. It is apparent that there are very minimal discrepancies in the nature of the two graphs. This suggests that the spring constant has decreased minimally with an increase from 25 to 200 degrees, and thus very little efficiency change is experienced by the two systems. In similar fashion, when reviewing the same relationship at temperatures of 25 and 400 degrees respectively, the change in time taken to reach zero displacement between the two systems is minute. At 600 degrees, there is still no clear discrepancy when analyzing the time taken to reach zero displacement. However, when the temperature is increased above 700 degrees, the nature of the graph begins to change dramatically, and the time taken to reach zero displacement decreases accordingly. This suggests that at this temperature, the spring constant begins to be negatively affected in that it experiences softness and thus reduces the strength of the spring, defeating its ultimate purpose. This is supported when reviewing the spring constant relationship with temperature as previously identified. It is apparent that after 600 degrees, the spring constant begins to decrease rapidly and vigorously, suggesting that the optimal temperature range for such system would occur before this temperature.
We can then suggest that the optimal temperature range for a system of such nature would exist between 25 and 600 degrees Celsius. Whilst the displacement reaches zero at a quicker rate with increased temperature, a reduced spring constant significantly influences the force that the spring can withstand. This is clear when reviewing the equation for force, which highlights the proportional relationship between the spring constant and displacement. You can see that as K is reduced, if you multiply that by the displacement, this will give you a smaller value for F. As practicing engineers, it becomes increasingly important to consider making alterations in design when optimal temperatures cannot be achieved. Ensuring that material used in the spring has a low thermal conductivity will increase the amount of temperature that it can withstand before experiencing softening and creep, and therefore increase its ability to perform at high temperatures where possible. A ventilation arrangement around the spring system that mitigates the compounding effect of increasing temperature will also serve as the same purpose. These systems can be very expensive though, and are only implemented if the thermal conductivity of the material cannot be changed and or investigated.
That completes our presentation. I hope you've been able to adequately gauge many of the principles discussed throughout and how MATLAB has been utilized as an important tool to understand and manipulate many of these mathematical concepts. Thank you.
Thanks for watching, Pete.